Okay, so I return the record. I'm talking, but I can't see that the recording has started, so I may be repeating myself. But anyway, Baosheng Li, now a faculty at Sun Yat-sen University in Zhuhai, has been writing a series of articles on the processes that are important for northward propagation of the interseasonal oscillations during the boreal summer. We've discussed the idea of boreal summer ISVs, interseasonal variabilities, and mesos, monsoon interseasonal variabilities, and we have talked about the background state. So if you look at April, May, you are transitioning from the northeast monsoon during the boreal winter months into a bit of a chaos, weak winds, and transitioning into southwesterlies. And there are some studies now also by Baosheng and others showing that the Middle East warming is beginning to shift these winds and so on. But in the intraseasonal variability context, we basically want to remember that there is this mean state with southeasterly winds, the trade winds here, which turn across the equator into southwesterlies, bringing boatloads of moisture into the Indian subcontinent. You have the marine ITCZ that stays here because the ocean is still warm, and you have lots of convective activity here, and you have convective activity starting here that is trying to propagate eastward but then gets detoured northward. So what are the processes that control these northward propagation? In the mean, we know that there is equatorial or tropical convection and terrestrial subtropical convection over the Indian monsoon region, and they are kind of oscillating between them. So when there is subsidence over the Indian subcontinent, you have the so-called break period, and there is typically convection in the deep tropical Indian Ocean. And when there is convection over the Indian subcontinent, you have the active period, and you have subsidence over the deep tropical Indian Ocean. So we call this the local Hadley cell, and it's not simultaneous, right? So convection happens, then it begins to propagate northward, and then it establishes over the Indian subcontinent, stays for a few days to few weeks, and then dies out, and then the convection moves back south and so on. So what are the processes that are important? If you just took some indicator of the ISVs and decided that the deep tropical convection is important, of course it is important, but in what way? So then you diagnose CMIP6 models saying those who do the deep convection in the tropical Indian Ocean do monsoon better. Of course they will do better because they are in some way also improving, let's say, the propagation. But unless you look at the propagation and the processes, then it can lead to wrong conclusions about what is actually in control of the interseasonal variability, and that's what Baosheng has been focusing on. So he starts Baosheng's paper. We will look at next. This older paper on structures and mechanisms of the northward propagating boreal summer interseasonal oscillation was by Jiang, Tim Lee, and Bin Wang. And they basically talked about the vertical shear. So the spatial and temporal structures of the northward propagating boreal summer interseasonal oscillations are revealed based on the analysis of the ECM4 model simulation and the NSEP and CARV analysis. So this is important. You want to do some diagnosis from the reanalysis, look for mechanisms, and then see if the models are capturing it, and then whether you are doing it in a coupled model or AMIP run or SST forced atmospheric simulation, you can get some interesting differences but important insights as well. The BSISO structure and evolution characteristics simulated by the model bear many similarities to those derived from NSEP and CARV analysis. Most notable features are the remarkable meridional asymmetries relative to the BSISO convection in the vorticity and specific humidity fields. So these are always critical because you have propagating systems, which means you have cyclonic and anticyclonic systems, convection and subsidence, and you have moisture loading, of course. A positive vorticity perturbation with an equivalent barotropic structure appears a few latitude degrees north of the convection center, the maximum specific humidity also shows a clear northward shift in the lower atmosphere. So they're basically trying to explain how the vorticity, humidity, and near barotropic structure are going to lead this process of northward propagation. Two internal atmospheric dynamics mechanisms are proposed to understand the cause of the northward propagation of the BSISO. The first is the vertical shear mechanism. The key process associated with this mechanism is the generation of barotropic vorticity due to the coupling between the free atmospheric baroclinic and barotropic modes in the presence of the vertical shear of the mean flow. So the mean flow that we looked at has upper level winds in the other direction. So you have basically vertical shear, and obviously when you have vertical shear you can curl your fingers around them and you get your thumb pointing to the direction of the vorticity, and easterly shear will give you easterly, so you are going from east to west, so you will get southward propagating or southward pointing vorticity, which we'll see in a minute. Okay, so the first is the vertical shear mechanism. In that sense, what happens then, the induced barotropic vorticity in the free atmosphere further causes a moisture convergence in the planetary boundary layer, leading to the northward shift of the convective heating. The second mechanism is the moisture convection feedback mechanism. Two processes contribute to the northward shift of the low level moisture. One is the moisture advection by the mean southerly in the PBL in the planetary boundary layer. Another is the moisture advection by the BSISO wind due to the mean meridional specific humidity gradient. The asymmetric specific humidity contributes to the northward shift of the convective heating. It's a lot of words, but we'll just look at the figure here. So you have northward direction here. Let's say this is the equator. You have eastward direction here and vertical, of course. So you have the vertical shear, and you can see the vorticity. So obviously you get horizontal vorticity, and if you have horizontal vorticity, you're going to have frictional convergence, let's say at the surface, and you can create convergence and moisture loading. So you have zeta prime anomalous vorticity setup that is positive, so cyclonic. So that's the barotropic and baroclinic coupling. And you have the vertical shear here, U1 bar up in the upper, let's say somewhere in the mid to upper atmosphere, and you have southwesterlies associated with westerly winds near the surface, and you essentially get the tilting of the vorticity because of the meridional shear of the vertical velocity. Where you have convection, you obviously have strong W prime, which is the intraseasonal vertical velocity. You can think of it as pressure or Z in this case, doesn't matter. So you have meridional velocity dropping off and turning negative, so that's going to tilt the vorticity down, whereas if you go forward you have again similar drop off and you're going to get the vorticity being tilted up. So you're going to create surface level convergence, moisture loading ahead of it, and that's the main mechanism of this Jiang et al. Mechanism, main process of the Jiang et al. Mechanism. And this, some paper followed after this with Bellon and J. Srinivasan, showing that this formulation had some issues near the equator. It doesn't explain the propagation near the equator. It works well after about 10 north or so because of the assumptions they made and so on and so forth. So the second part of this story is that the idea of where the energy comes from actually was kind of reassessed by Leizhou and others here, and I was part of this story, just for full disclosure. So here they argued that there is not only a Hadley cell in the meridional direction, local Hadley cell here, but you also have the local Walker cell. So you have deep convection in the western Pacific maritime continent, which can produce subsidence over in the western, tropical Indian Ocean, and that's what is shown here with this red arrow. that can generate warm SST anomalies by clear skies, weaker winds, etc., and ocean processes involved as well. And that gives you a coupled sea surface temperature zonal wind, meridional stress in the zonal winds. And the first EOF of the daily SSTs and winds gives you something called the Central Indian Ocean mode that's discussed, and that time series of that EOF has high correlation with intraseasonal rainfall here, and that was argued to be important. So in this case you are going from vertical shear to horizontal shear being the main energy source, at least for northward propagation. But the northward propagation itself was explained by Bao-Sheng Li in several papers by now. This is the latest one that I'm going to use. The role of vorticity tilting in northward propagating monsoon intraseasonal oscillations. Actually this is a little bit older, 2021, so we'll come back to the 2025 paper in a minute. What is the plain language summary here? The northward propagating monsoon intraseasonal oscillation transports heat and momentum from the tropics to subtropics during the Indian summer monsoon, but a poor representation of meso is still a glaring shortcoming for climate models. Here the results show that vorticity anomalies lead meso by about 5-degree latitude, and the tilting of vorticity is important. Tilting of vorticity is an important component in the vorticity budget and plays a key role in the northward propagation of meso, although the vorticity anomalies are in a balance between their components. During the Indian summer monsoon, the vertical shear of the background zonal wind sets up a background horizontal vorticity, which we already looked at, which is then tilted in the vertical tilted by the vertical velocity during meso, so the meridional shear of meridional gradient of the vertical velocity. Due to the meridional gradient of vertical velocity, to the north of the convection, positive vorticity anomaly is generated, while to the south a negative vorticity is generated. So that gives you convection ahead of the present convection and the northward propagation. So updraft is induced to the north and downdraft to the south. In the 19 phases of In the 19 phase 6 of coupled intercomparison project CMIP6 models, most models do not reproduce the tilting during ISM. Since the northward propagation of meso depends on vortex tilting, most models yield a poor rendition of meso. As a result, the intraseasonal rainfall and mean rainfall during ISM are still much weaker in CMIP6 than in observations. So note the words here. It says vortex tilting is an important process. It doesn't say that controls intraseasonal variability. So if you look at tropical convection, and that's important, you have to say that's important part of the meso and not that controls intraseasonal variability, right? So there is a process of convection over land, over the ocean, and how they are out of phase, but with a lag, because you have communication via these propagating systems, and in the propagating is where you get this vorticity tilting. So just to simplify, you are looking at the free troposphere, you have easterlies and westerlies, so you still have the easterly vertical shear, which gives you the horizontal vortex tube as we saw before. But now the meridional gradient of W, there is the convection which lifts the vorticity, vortex tube if you wish, and it is lifted less on this side and this side because of the gradient. So away from the convection, vertical velocity falls off, but here you have del omega del y, so pressure coordinate is greater than 0, and del omega del y is less than 0 here compared to the convection center. So you induce an anticyclonic vorticity here and a cyclonic vorticity here. So it's the same process as Jiang et al., except some details are put in, and this now explains the propagation all the way from the deep tropics into the Indian subcontinent, so removes some of the limitations of the other model. And Bao-Sheng Li has extended this work. I'm being very brief. There are lots of equations involved in understanding the budgets and the moisture loading and the tilting term. You can do vorticity budget and show the role of the vorticity advection versus vorticity tilting, and you can do the mean advection of the anomalous vorticity versus anomalous advection of the mean vorticity and so on. And what he did then was to extend this into the South Asian monsoon and Western North Pacific monsoon, and again do the convection and vorticity relation by extending the analysis to show that while in the monsoon region the tilting that we talked about dominates because the winds are mostly westerly in the lower level, and that's what we talked about here, and there is a shear but surface low level winds are westerly in the low level jet, the Finlitter jet and so on. But as you go towards the east, actually you begin to have more of a southerly component south of 10 south, north of the equator. So here northward propagation is dominated not only by vortex tilting but also by the advection term, and in fact by the time you get into the open ocean here, it's the advection term that is dominating compared to the tilting term. So we have to really be careful about how we say what is controlling ISVs, okay, because we still don't know that. What we can say is that there are tropical convective systems here, and they are interacting with subsidence and ascent, and there is a convection here and here which are also interacting with each other by ascent here, subsidence here, ascent here, subsidence here, and so on. In between you have these propagating systems. So we don't really answer all the questions, but I just wanted to make this point that if you look at the vorticity tilting mechanism, and okay, this is a different point that I didn't want to get into here, but let me leave that. That's got more to do with how the meridional gradient in SST in the Bay of Bengal is actually feeding into the northward propagation. There is the pressure adjustment mechanism, and then there is a vertical mixing process of momentum, because if you have cold and warm SST anomalies at intraseasonal timescales, there is a hydrostatic pressure and pressure adjustment mechanism, but you also have vertical mixing of momentum, which is more important. So I just happened to put it in the wrong place from another lecture. Okay, so the main point here is that we have to be careful how we diagnose what is really the critical process for boreal summer interseasonal oscillations, or even for MJOs as such, because what processes are important and what controls the ISVs are not the same. So we have to just keep on diagnosing the mechanisms and look at northward propagation, which is actually the most intrinsic character of the boreal summer interseasonal oscillations, because this started way back when Bin Wang and Tim Lee and so on started proposing that maybe there are Rossby waves coming from the west-northwest Pacific into the Indian region. It turns out there are 10 to 20 day modes that come in, but they also have 30 to 60 day modes that are propagating northward, and then people have used the words like primary and secondary and so on and so forth, but let's not get into that. I hope the point is clear. As I said, I'm being very brief, but the papers are available, so definitely follow up if you want to understand the diagnosis in a deeper sense. And once you do that from reanalysis, you go back to SIMIP 6 and show that those that are doing the vorticity tilting mechanism properly are doing the monsoon much better. So you can't take that and say vorticity tilting controls ISVs. It just means that vorticity tilting, vortex tilting and vorticity advection are very critical processes for northward propagation and depends on where you are. Okay, so let's leave it at that.